video, we have talked about a limit of functions of several variables. It says that if you have a function that's defined over domain D, which is a subset of R square, where D is an open set, which is a real valued function, and this AB point, it has to be in this D, and for every epsilon greater than 0, there exists a delta greater than 0 such that 0 less than mode of x minus a less than delta and 0 less than y minus b less than delta will implies f of xy minus L is less than epsilon. So this is the epsilon delta definition of a limit of a function, and then we can say that the limit of f of xy as xy tends to ab will be. So with that, we have also shown that if you are approaching, if this limit is exists, then the approaching to the point AB is independent of path. If you have, this is the domain D, and there is a point AB in that, and there is a neighborhood. So to approaching to the point AB, if all paths have the same answer of that limit, then we can say that the limit is exist. So in the previous lecture, we have discussed that if it is independent of path, that means you are approaching to this point by different paths, and the answer of limit of this function is different, then we can say that the limit does not exist. So with that note, here in this lecture I am just extending that same topic as repeated limits and the iterated limits. Both have the same thing. So repeated limits and the iterated limits of this type of function is defined as limit of x tends to a, limit of y tends to be f of xy, and limit y tends to be limit x tends to a f of x. These two limits are known as the repeated limits and iterated limits or iterated limits. So it is known as the repeated limits, or another name is iterated limits. So let's have the example. If f of xy is equal to x minus y upon x plus y, x plus y is not equal to 0, because this denominator is, this function is exist if x plus y is not equal. That is the domain of the function or set of all xy where x plus y is non-zero, and let's say it is 0 if x plus y is 0. So the question is, find the repeated limits at point 0. So at point 0, 0 we need to find out the repeated limits. So as per the repeated limits as we have defined earlier, that are these limits, and you can observe that at point 0, limit y tends to 0, x minus y upon x plus y is there. Now to substitute means to take this limit, this is a case of one variable where your x is a constant, treated as a constant, and y you are taking a limit at y as a tends to 0. So that will gives me limit x tends to 0, x minus 0 upon x plus 0, and you can say that this is the limit x tends to 0, x by x, that is x is cancelled out, we will have a one answer. And on the other side, if you have the other limit, limit y tends to 0, limit of x tends to 0, f of xy is equal to limit y tends to 0, limit x tends to 0, x minus y upon x plus y, that is limit y tends to 0, you'll have 0 minus y upon 0 plus y, because you are taking the same manner as above. Your y is treated as a constant and you are taking limit x tends to 0, so that's why it is 0 minus y upon 0 plus y. That will give me y tends to 0 minus y upon y, that will cancel out, so the answer is minus. So here the one repeated limit is 1, another one is minus 1. And also you can just observe that the limit of the function as this f of xy, that we have limit xy tends to 0 0 x minus y upon x plus y, as if you choose your path y equal to mx, because this is the same degree in the numerator and the denominator you will have. If you choose the path y equal to mx, your f of x mx will be x minus mx upon x plus mx, and you can just see that x will be cancelled out and it's common, so it is 1 minus m upon 1 plus m. And so the limit of that function xy tends to 0 0, f of xy is depends on m. So what we can see here, what is actually what we are doing in this, we have this 0 0 point is here, and you are taking x tends to 0 means here you are approaching the x is tending to 0 on this side you are taking, and y is tending to 0, that means you are traveling first through x axis and then y axis, and in the other repeated limit first with y axis and then traveling to x axis. So also it is the same thing, it is about the path independence and dependence of the limit. Limit is exist, it is a independent of path. Example, and with this remarks we can note that if limit of the function f of x y is exist, then we can say that this is the remark we can write. It says that limit, these repeated limits are actually exist and they are equal, and they are equal to the limit L. If this limit is exist, then the repeated limits are exist and they are equal to L. So what will be the contrapositive statement of that? What do you mean by contrapositive statement? That means if P implies Q, that is the statement, that not Q implies not P, that is a contrapositive statement. That means if this repeated limits are not equal or they are not exist, then we can say that the limit is not exist. So that is another way to check or existence of repeated limit is there. So that is the second remark I can write is, that means the repeated limits are not equal, or if they are not exist, then we can say that the limit of function f of xy as xy tends to 0 0 is does not exist. So this is another way to check whether the limit is exist or not. So let's have the example with that. So prove that this limit 3x plus 4y upon 3x minus 4y as xy tends to 0 0 does not exist. See, you can check this limit is does not exist by taking y equal to mx, and you can do that. The another way is you can check with the help of this repeated limits, so that you can take limit x tends to 0, y tends to 0, 3x plus 4y upon 3x minus 4y. So that is limit x tends to 0, y tends to 0, you can take it is 3x plus 4 into 0 upon 3x plus 4 into 0. So that will gives me 3x upon 3x, and 3x upon 3x will give me answer 1. And if you have y tends to 0, limit x tends to 0, 3x plus 4y upon 3x minus 4y, that will gives me y tends to 0, 3 into 0 plus 4y upon 3 into 0 minus 4y, so that will cancel out 4y, so you will have 4y upon minus 4y, so that is answer is minus 1. So you can say that these repeated limits are not equal, and so therefore the limit of the function at 0, 0 does not exist. So this is another way is to check whether the limit is exist or not. With that we can move further and we can state some of the results of a limit which we have, which says that you have a domain D which is a subset of R and it is an open set I am considering. If f and g are functions defined on this, and if the limit of these functions f of xy at point AB is L and the limit of the function g of xy is M, then you have certain results. The first one is the limit of sum is sum of limits, so that means f plus g at xy will be L plus M as xy tends to AB, and if it is minus here, here is also minus. Second result is limit f into g at xy will be L into M as xy tends to AB. The third results I am saying is if you have the number R which is a real number, so if limit of R into F at xy will be RL as xy tends to AB. If you can multiply a function by R, that R you can take out from the limit, that is the meaning of this. The another one is f upon g at xy will be L upon M xy tends to AB, provided the g is non-zero. The proof of this results we are not discussing, but it is very important to calculate the limit. For example, the example is given: compute limit of x plus y upon x minus y at point 1, 2. So using this above four results we can state this, or we can find out this. If I consider f of xy as x and g of xy as y, then you can say that the limit of this function f of xy at point 1, 2 will be 1, because f of xy is x and x goes to 1, and limit of g of xy will be 2, because y tends to 2 we have here. Now if you want to calculate this limit x plus y upon x minus y as xy tends to 1, 2, we can see that this 1 plus 2 upon 1 minus 2, as we have seen, because the division rule already apply division rule here, addition rule here, subtraction rule here, we apply here, and we can get this is the limit, and the answer will be minus 3. So with that we can move further. We'll have another result is called the sandwich theorem. As you have sandwich theorem for one variable also, we have considered the D which is a subset of R, which is an open set which contains the neighborhood of AB, and AB is the point which is in this D. If you have this f, g and h, they are the functions, real valued functions defined on D, and also you have this g of xy is less than or equal to f of xy is less than or equal to h of xy for every xy in D, or I can say it is the intersection with ND, a neighborhood of AB and D. And if also there is a given is limit of g of xy as xy tends to AB is equal to limit of xy tends to AB of h of xy is L, then we can say that the limit of f xy is also L as xy tends to AB. The things is the limit of this function and the limit of this function is L, then the limit of the middle function is also L. Okay, so that is the sandwich theorem that you probably know. Now next one is compute limit of xy tends to 0, 0, tan inverse of xy upon xy. So here if you are trying to compute this limit, what will happen is if you substitute or if you can take the limit here directly, it will have 0 upon 0 form. So you cannot able to calculate this limit directly. So you have to do something. So here what I am using the mean value theorem. So Lagrange mean value theorem which I am using, and it gives me the inequality will be 1 minus phi cube upon 3 less than tan inverse of phi by phi less than 1. See, if you want to prove this one, just multiply this inequality by phi. So you'll have the equation or inequality will be this form. If you multiply both sides by phi, you have this is the inequality you have, and then you will define a two function. The first function is psi of phi will be tan inverse of phi minus phi, and psi of phi will be defined as tan inverse of phi minus phi plus phi raised to 4 by 3. You can prove that this function is decreasing and this function is increasing, and then you know how to prove that we have done in your calculus course. Using that you can prove this inequality we have. Now what I'm just replacing this phi by xy, so you'll have the xy cube upon 3 less than tan inverse of xy upon xy less than 1, and then you will take the limit both sides. So you can just check that the limit of this side will be 1 as xy tends to 0, 0, and the limit, this is already constant quantity, so that's why a limit by sandwich theorem. So we can say that by sandwich theorem, a limit of xy tends to 0, 0, tan inverse of xy upon xy is 1. So that's it for this video. Let us recall what we have did in this video. We have defined the repeated limit, or we can say it is the iterated limits. So we say that if the repeated limits are not equal, then the limit is not exist. Limit is exist and the repeated limits are equal, and that is equal to the limit. That is the two remarks we have seen. We have seen that the limit of sum is sum of the limit. Same results for product, division, and if you have a scalar, also you have a same result. Lastly, we have seen one of the theorem. It's called the sandwich theorem, and the example related to it. So that's it for this video. If you have liked this video, please press the like button. If you have any comments, suggestions, or questions, please drop down in a comment box. Thank you very much. Bye bye.